So colligative properties are properties that are physical properties, and they are interesting in that they only depend, I can't spell properties, and they only depend on the concentration of the solute, not the identity. Okay, and if you think, well, that's kind of weird, ask yourself, okay, if this is a glass of water here, okay, and it was glucose, so let's say it was one molar glucose, would you drink it? And I'm guessing most of you would probably say, sure, okay, I'm not really a big fan of glucose, but I could certainly slurp it up, no problem at all. And if you took the same glass that was 1 molar formaldehyde, would you still drink it? And most people would say, are you crazy? Who's going to drink formaldehyde? Formaldehyde is the stuff that you use to pickle yourself when you're dead, so you don't mold when you're on display in the coffin, right? Who's going to go ahead and drink formaldehyde? Even though it's the same concentration, clearly it matters what it is. Formaldehyde is very dangerous for us to drink. Glucose is relatively harmless for us to drink. Well, colligative properties are properties that only depend on concentration. So from a colligative property standpoint, whether it's glucose or formaldehyde, it has no matter whatsoever as long as it's the same concentration. There are a series of colligative properties. We'll talk about 3 in this course. And the first one is boiling point elevation. So boiling point, so that's the temperature that the solvent boils at. Elevation, elevators go up. And it turns out that boiling points tend to go up as well when we dissolve things in here. So for instance, most of us are pretty happy with water. Water has a boiling point of 100 degrees Celsius at regular pressure. And it turns out that if you go ahead and you take 1 molar glucose and you boil it, it boils at very approximately 100.5 degrees Celsius. If you take 1 molar formaldehyde, that's stuff that you certainly wouldn't drink, and you try to boil it, it would boil at essentially exactly the same temperature, 100.5 degrees Celsius. If you had 1 molar boogers that were aqueous, so dissolved in water, I'm not exactly sure how to measure out 1 mole of boogers in 1 liter of water, but if you did, let's say we would predict it would boil at exactly 100.5 degrees Celsius. And so when we look at these, right, we can see that these have all increased in boiling point over pure water. In fact, we can see that all of these have what we call an elevation of 0.5 degrees C. So this is the boiling point elevation, 0.5 degrees C. You might wonder, well, what happens as we increase the concentration? As we increase the concentration, we increase the boiling point. Let's go ahead and take a look. So we saw in the last slide that 1 molar anything boils at 100.5 degrees C. If it's aqueous, I should probably note. Okay, so that means it's dissolved in water. That's an elevation of 0.5 degrees C. You might guess what happens with 2 molar glucose. And 2 molar glucose, again, if it's dissolved in water, boils at 101 degrees C. So that is an elevation of 1 degree above its normal boiling point. You can guess the pattern, I'm guessing. If it was 3 molar in glucose, it would boil at, can you guess? Yep, 101.5 degrees C. That is an elevation of 1.5 degrees C. And if we had 4 molar, you name it, so 4 molar, boogers, then we would predict that it would boil at a higher temperature, 102 degrees Celsius, which is an elevation of 2.0 degrees C. So we can see that the boiling point elevation is proportional to the concentration. And this first symbol here just means proportional to. And this second symbol here, right, when we have those square brackets, that is telling us that it is the molar concentration of whatever is inside. So the bigger the molar concentration, the bigger the boiling point elevation. Okay, are you ready for something neat? All right, we have some puzzles, and this took people a long time to figure out. And let's see if you are smarter than scientists from 100 years ago. Take 1 molar sodium chloride, and you might expect the boiling point would be the same as 1 molar glucose, but it turns out it actually is the same as 2 molar glucose. It boils at 101 degrees C. Huh, that's weird. Okay, well, what about 1 molar calcium chloride, CaCl2? Again, we said before, right, the concentration is the thing that determines the boiling point elevation. If they all have the same concentration, they should all be elevated by exactly the same temperature. However, when we measure its boiling point, it is 101.5 degrees C. So this is a puzzle. So the 1 molar salt behaves in many ways as if it's 2 molar glucose. The 1 molar calcium chloride behaves in many ways as if it's 3 molar glucose. So what is going on here? Well, it took people a while, and people did not believe it initially, but let's go ahead and go to another slide and see what is going on here. So our 1 molar sodium chloride is behaving like a 2 molar solution, and our 1 molar calcium chloride, and these are both aqueous by the way, is behaving just like a 3 molar solution, at least when it comes to boiling point. So what the heck is going on here? Well, it turns out that the thing that we haven't taken into account here is the sodium chloride, when it dissolves, is actually breaking down. Remember our full ionic equations from last week, and it is breaking down and forming sodium ions and chloride ions. And if you've got 1 mole of sodium chloride in a liter, and you break it down, for every one of these, we'll make one of these. Remember we said before you could go ahead and take your hands and you could point. So that gives you that 1-to-1 ratio. And also the sodium chloride to chloride is a 1-to-1 ratio. So that tells us that for every 1 sodium chloride, we will have 1 sodium, and we'll have 1 chloride, and again, it'll be in a liter. And so what we need to do now is we need to remember that the colligative properties are proportional to the total concentration, and the total concentration of 1 molar sodium chloride is actually 2 moles per liter, right? So this is the total concentration. The solution does not care that the sodium chloride we write on the page as NaCl. It only cares the fact is that when it dissolves in water, it is breaking down and making 2 things. In the same way, if you buy a Twix bar, you get 2 bars inside. You don't get just the 1, you get 2. Doesn't matter, it came in 1 packet. It breaks down and gives you the 2 things. So that total concentration is really what we need to care about. We call this actually the osmolarity. So the osmolarity is the total concentration, and sometimes we write that as 2 osmolar or 2 OSMOL, or osmol for short. So sodium chloride behaves in many ways. A 1 molar solution is if it's actually 2 molar. And I bet you can guess what comes next, right? So what about that 1 molar calcium chloride? It's behaving as if it's a 3 molar solution. And the reason is that when that calcium chloride dissolves, it actually can break down and form 3 things. So it can break down and form calcium with a 2 positive charge. It's in group 2. And those chlorides, remember, right, they don't stick together. They have same charges, so they repel each other in solution. And if we had 1 mole per liter of calcium chloride, when it dissolved, we would end up with, let's go ahead and get our fingers again. So for every 1 calcium chloride, we'd have 1 calcium. And for every 1 calcium chloride, we'd have 2 chloride ions. So you get 1 mole of calcium in every liter, and you get 2 moles of chloride in every liter. And the boiling point elevation, that colligative property, depends on the total concentration. And if we had 1 molar calcium chloride, it would give us 3 molar of stuff. So our total concentration is 3 moles per liter. And I guess we could call that 3 molar, or we could call it more properly 3 osmolar. So it behaves as if it's a 3 molar solution. So here's an interesting puzzle. What's the osmolarity, the total concentration of ions in 0.2 molar iron 3 nitrate? So iron 3 nitrate, so it's a soluble ionic compound. All nitrates we saw in the chapter 6, right, are soluble. That means it breaks down and it forms ions. So we, of course, don't know iron's charge, but we do know that it comes with 3 nitrates, and the 3 nitrates carry a charge of -1 each. So that means that if you got 3 of them, that's -3. So the iron actually has to have a charge that cancels it out. That's +3. So we can write it something like this. What is 0.2 molar telling us? That means that there's 0.2 moles in every liter of iron 3 nitrate. And we go ahead and we look at it dissolving, and we can say for every one of these, we would have the same number of these, but for every one of these, we would have triple that number of nitrate ions. So the iron on the other side is the same number, but the nitrate is 3 times bigger. So 3 times 0.2 is 0.6 molar. And again, the total concentration is what we care about here. The total concentration, 0.2 plus 0.6, is 0.8 moles per liter, or molar, or more properly, we can say it is 0.80 osmolar. So 0.2 molar iron 3 nitrate actually behaves as a 0.8 molar solution when it comes to a colligative property. So one more example of a colligative property is freezing point depression. So we know, for instance, with water, water freezes normally at 0 degrees C under normal atmospheric pressure. We can actually go ahead and dissolve things in water. So if we've got 1 molar sodium chloride, actually that's a bad one to start with. I shouldn't have picked that, should I? So let's start with something that doesn't break down into iron. So 1 molar glucose. And if we measure its freezing point, it actually freezes at about -2 degrees C. And if we have 2 molar glucose, we said before, right, these colligative properties depend only on total concentration. So it will freeze at -4 degrees C. So now I think you see what we're on about here with depression. So this actually is a depression of, well, let's see, it starts at 0 and it goes down to -2, so it went down by 2 degrees. And in this case here, it went down by 4 degrees. So the freezing point depression is the temperature it goes down by. We might also go back to 1 molar sodium chloride. And remember, in wintertime, we add sodium chloride to our sidewalk to melt the ice rather, and turn it into water. So the reason we do that is that when we add salt to water, it depresses, it lowers the freezing point. So on a day, right, if we lower the freezing point and our room temperature or our outside temperature is above the freezing point, it'll melt. So 1 molar sodium chloride, because sodium chloride actually breaks down into 2 things, right? It breaks down into sodium and into chloride. So if this is 1 molar and it breaks down into 1 mole per liter of each thing here, that gives us a total concentration of 2 molar. So what will its freezing point likely be? Will it be like the glucose that's 1 molar or the glucose that's 2 molar? And the answer is it behaves like the 2 molar glucose because it's 2 osmolar. So it actually would freeze at -4 degrees C. And if you like, that has a freezing point depression of 4 degrees C. So the more things the ionic compound breaks down into, the better it is at depressing the freezing point. So if you buy the super duper ice melt in wintertime, instead of getting the sodium chloride that breaks down into 2 things, the super duper ice melt is calcium chloride that breaks down into 3 things. Because calcium chloride now gives you 3 times the whammy of, say, a molecule like sugar or glucose would, let's say.